Welcome to another exciting, fun-filled COMP1511 lecture. Yay, computing is awesome. Welcome to week 12 as well. Shh. Welcome to week 12. There's nearly at the end this week, next week, then it's all over, just about. Today, that button, cool. So we're going to look at some really cool stuff today. We're going to look a bit more at memory layout of things, but sort of more importantly, not just what is the memory layout, but why is this really important, and how can this lead to really bad things happening in your code, and how did Andrew manage to win the Fun Aqua tournament with a score that was mathematically impossible? I came second, whatever. And yeah, cool. Admin stuff, assignment 3 is out now. Who has not started the assignment yet? You make me cry. Can you start the assignment tonight, please? So actually, a thing with the assignment, if you take your code from the lab that's due tonight, the week 11 lab, questions 2 and 3, I think, like the fruit bot go west and the petrol one, you have an AI, congratulations, you started the assignment, make it a little bit smarter, and then you'll be off to a good start. So that is due tonight. The weekly test is due on Friday. Don't forget about help sessions, everything is great. I've set up a question thing for the lecture on Echo 360. I think I have about an hour worth of stuff today, maybe an hour and a half, so I'll spend the rest of the time answering whatever you think is useful to talk about, not just whatever I think should be good to talk about. Has anybody tried to get into this but couldn't get into it? Only one person, maybe. Has anybody managed to get into this so far? Because I can see there are like 8 questions here, so clearly 8 of you can. But yeah, you get a boxy thing like that, write some things, awesome. So let's talk about memory in C. I know we've talked about this a bit already. Everything is in memory, right? When you have your program, things that are in memory include your variables, right? Because variables have to go somewhere. Things like memory, your Malloc is in memory, but also things like the code that you've written is in memory, which will be important shortly. So I had a diagram back a few lectures ago. And so this is sort of like a almost not broken this time diagram. So at the top we have, it says libraries and magic, various things that you don't need to know about. Below that you have your program. So the actual compiled machine code for your program is loaded into the memory of your program. We then have the heap, which is where things, dynamic memory goes, so things like memory that's been Malloced. We have the stack, which is where things in your functions go, function variables and so on, and then some more magic down the bottom. That one. Cool, and some terminology. I've referred to function memory, and what that actually means is the stack. And then dynamic memory, or then the magical cloud where Malloc puts its memory, is also known as the heap. Cool. So like I said, every function has its own memory, and we call this a stack frame. Let me do the drawing thing. Draw on screen. Cool, okay, so every function has its own memory, right? So if we have a program int main, int I equals 0, if that's at all readable, right? So main has its own memory, the memory for the main function, and that contains the variable I. So in this case, the number 0. Cool, does that make sense so far? Like this is revision from what I've said over and over again. Functions have their own memory. Cool. And so inside the stack frame of a function, it's got more than just the local variables of that function. Let me, oh no, where did the drawing go away thing go? That one. So let me grab some really basic code. And I'm trying out a new thing with the code today. So you know how I code live and you can see the code as I write it? I'm coding on my Chromebook, but the files I'm editing are in the live folder, so you should be able to access them still, hopefully. But let me know if things do not work. Here's a Hello World program. Hopefully you're all very happy with this. Let's change it to equals 0. Cool, and so the stack frame for this function. Okay, cool, everything is working now. Everything will continue to work for the rest of the lecture. Shh. So as I've sort of explained at a higher level before, right, we have main has function memory. So when we have the main function, it has its own memory down here. Thank you. It has its own main function down here. So it has a box for I and a box for j. Cool. We set I equals 10, so call 10 as in here. We then call the function foo. What happens here is the function foo now starts, it has its own function, it has its own stack frame, we call it, its own function memory. I'm going to draw it here. So it has a variable called x, which just contains 20. But there's actually some more stuff than just the local variables, right? So the local variables obviously have to go there. But given that when we call a function, right? And so the control flow of your program jumps to another part in your code. So if you think about your, this code here, right? The code for main will be somewhere in your program's code. Like the machine code for foo will be somewhere. When it hits this point here, when it goes in j equals foo, what it needs to do, it needs to jump from where it is to the place in the code that is the code for foo, right? And so it'll run through that code, it'll do that code, and then when it's finished, it needs to know where it started from, so where the rest of the code for main is. So we have a couple of things in here. Let me make that smaller. So one of them is called the return address, and I'll just write that for now. And so the return address is the address of the place in the function that it got up to. So for example, the return address, what's up? Ah, let's get a different color. That's worse. Orange is good? Cool. Cool. Is that visible now? Awesome. So the return address is going to be, right, the location of this code here, where it got up to. So when it's running through the code, the compiled like machine code from main, it'll go, I'm about to call foo, so I'm up to this part of the code, like the compiled machine code. It'll then jump to wherever foo is, execute that code, and then when it's finished, it's going to go back to whereabouts it was up to in main. Right, so does this make sense so far? It needs to know where it was up to when it called the function so that it can go back there afterwards. So that's called the return address. There are a couple of other things. In terms of the stack frames themselves, it needs to know how big these are. And so they have like sort of the address of where a stack frame starts and ends, which is called the base pointer for the bottom and the stack pointer for the top. Don't freak out about like memorizing all this stuff. I'm just sort of explaining how it works, which will be relevant shortly. So there's the base pointer saying this is the bottom of the stack frame, the stack pointer saying this is the top of the stack frame. And so also in this bit here, so inside foo's stack frame, is information about where the stack for the function main was. So is this all good so far? The important thing to take away here is that within the stack frame of a function, within the function's memory, it has both the local variables and information about things like where the previous stack frame is, where the previous function's memory is, whereabouts you were up to in the code when you called this function, and so on. So is that all good thus far? Cool. Slides. Did I forget it? I didn't compile the code on any prototypes. I had a prototype though. I had a prototype in the previous version I typed. Whatever. So the start and end of the stack frame, like you need to know where your local variables are and where to go when the function returns. So whereabouts the control flow of code is going to return to. What if these are incorrect? What if I somehow magically had the power to change things in your program memory? So hypothetically, I can just edit your memory at will, hypothetically. What could I change about the memory in your function to cause very bad things to happen? Let me see another color. Is the light blue readable? Cool. So what if I change the return address? What if I manage to overwrite the address of where you're going to go back to when you're finished? So rather than saying you're going to go back to main function here, I say you're going to go back to my other function that I've written that does malicious, evil things, right? So I guess what I'm trying to say is this information is important, and the fact that it's here means if you have some way of changing it, like accidentally or maliciously, you can do bad things. Like C is a very low-level language. We can do there's no safety checks, there's like no safety whales. You can blow your own foot off if you want. And one of the things that you could do here is destroy that. And so in terms of how this could happen, like how could you end up changing memory? Arrays, right? Arrays are nice. We learned arrays early in the course. They're very straightforward, simple, no danger at all, right? Except wrong. So I prepared a demo earlier, and it worked earlier, which guarantees nothing. Cool. So I'll just walk through the code briefly. I've got lots of printfs and stuff, but basically, this code has an array of some size. It lets you make changes of the form array sum index equals value. So you give it the index, you give it the value, and it'll set that array index to be that value. Right? So if I told it set array index 0 to be 5, the array would have 5 and then whatever else. You're allowed to make the same number of modifications as the size of the array. So I'll let you, the array is 5 big, you can do 5 of these operations. In terms of why you would want to do this, maybe arrays are fun, maybe you want to play with an array interactively, whatever. And this is going to be an example of how things might go wrong. So I might actually start with GCC. DCC is like training wheels, and the real world people don't use DCC, but for now it's nice because it'll like stop you from falling off your bike. GCC will not do any of these things. GCC will let you do whatever you want. Cool, so welcome to the interactive array tool. Yay, this is great. You can make 5 array modifications of the form array index equals value. So let's set index 0 to have the value 5. So you can see the array is now 5, 0, 0, 0, 0. Cool. So if I set index 4 to be 2, my array now has 2 in index 4. Cool, this is all good and boring so far. What should I change? What index should I change? 6? Do you want to say 5 instead? Because 5 is just 1 off the end of the array. Right. That button. So this is our array, right? And it's 5 elements big, so they go 0, 1, 2, 3, 4. So if I set something at index 5, it's not part of the array, right? And DCC would be like, well, what are you doing? Illegal array pointer or other access, you monster. But GCC will happily let us do that. So let's set array index 5 to be -10. And I need to put this in full screen. Cool, can you see the bottom? You maybe can't see the bottom. Let me scroll down there. Cool, so I've set array index 5, so 1 off the end of the array to be -10. And my loop counter I is now -9. So we had before I is 0, I is 1, I is 2, and now I is -9. Right, like I've changed the value inside another variable that's not this array by using an array index that's off the end of the array. Right, and so you can now set another 14 array elements, so you have more array choices to do, which you didn't before, yay. Was that a question? Just a stretch. But does this sort of make sense? I can write over the end of my array, and then bad things will happen. What if I write really far over the end of my array? Array index 10. If I set that to this number, I can't see that it's changed in the array. The array is just 5 big. Nothing broke. Array index 100. If I set that to 100, nothing broke. That's disappointing. Array index 1000. Why is this not breaking? Cool. So I tried to access array element 10,000. My array is 5 big. 10,000 is not less than 4, so 10,000 is not in the array. So what's happened here? I have accessed something in memory somewhere far away that's not in my function's memory, and I've changed it to 100. And for some reason, this has caused problems. Segmentation fault is what you get when you don't have DCC and you have some illegal memory access type thing. So does this make sense? We can, one example of like a way to have, one example of a way that you can do bad things in your program, like illegal things, for example. So the C specification doesn't define what you should do if you go off the end of the array. Like it's undefined, it's not a thing that you're allowed to do. And so bad things could happen. Maybe it'll be fine, maybe it'll crash, maybe it won't crash. But maybe you'll have carefully like overridden some important thing to make some other thing do something else. Cool. So arrays, access out of the bounds of an array is one way that that can happen. And it gets even better. You can do even cooler things than just this. And one of the tutors, Curtis, has prepared a demo, which is even working, we hope. Cool. Okay, and so Curtis will run from his laptop a cool demo of using this illegal C sort of stuff to do even crazier things.
Hello, everyone. Sorry that took a while to set up. So Andrew was talking about how the information stored in memory is kind of important, and if it gets modified in any way, it can kind of lead to bad things. Shh. Good. And the question is, when would things get modified to things, when would the stuff in memory get modified to values that we don't want? Generally, the answer is when we let whoever's giving information to our program, anyone who's using our program, have complete free access to our memory. So we want to avoid that as much as possible. So, here I have a simple program. It's going to greet you, and then it's going to ask for your favorite number and tell you what your favorite number is. Pretty straightforward. So, greet. We have a buffer. This is just an array of characters. That's what we're going to read the name into. So we ask for your name, and we use gets to read in your name, puts it in the buffer, and we say, printf, nice to meet you, printf your name, then close it. For the favorite number, we have a buffer. We ask for what your favorite number is, type in your favorite number, we turn it into an integer and return it, and then our main function prints it out. So let's see what happens when we compile it and make. It compiles, get some warnings. Let's ignore those warnings. Vuln, enter your name. My name is Curtis. Nice to meet you, Curtis. What is your favorite number? My favorite number is 24. Favorite number is 24. What could possibly go wrong? Well, let's take a closer look at this code. You'll notice that I've set my editor up so it tells me some friendly things, like when I'm doing bad stuff. It says that, well, for one, it says that this function doesn't exist. For some reason, it doesn't want this function to exist. And it also says that this could be potentially insecure. Does gets exist? If I say man gets, well, there's a function there. read through the page. It's got some interesting stuff. If I look at the bugs section, it starts off with the words, never use gets.
The description does as well.
We'll be fine. Description does as well. Oh, description. Never use this function. This is a function which asks the user to enter in some text and it stores it into an array. What you should be concerned about is we have not told this function how big our array is. So what will it do if we try and type in more text than fits in our array? It'll just keep going, it'll write it all the way down the stack. And if we write it to an array that's somewhere inside of our function, that'll fill up the array. There might be some extra blank space at the end. But after that, it'll overwrite, I think Andrew mentioned the return stack point, the return base pointer, which is the information which tells us where the data for the function that called us was. And it could overwrite the return address pointer, which is the bit of information which tells us what code we want to execute once we finish this function. So normally that would just say, this is the next thing once you return, and it'll go back to the function it was in. But maybe with this, we can use it to insert our own code and get it to execute our own code. The other issue we had was Printf, and it said that there was some issues with Printf. There's not much here because I'm looking at the wrong one. Man3 Printf, please be the right one. Okay, this is a very long manual entry. But bugs. Code such as print foo often indicates a bug, since foo may contain a % character. If foo comes from an untrusted user input, it may contain %n. What's %n?
Write the number of bytes that have been written into the next integer type argument, integer pointer type argument.
CSN. The number of characters written so far is stored into an integer pointed by the corresponding argument. You can have a printf format that writes data into your program. That's nuts. Well, let's see how bad it can be. So if I write vuln that says if it contains a % character, something could go wrong. So what happens if I do %d? Nice to meet you, -135177043. That's not my name. I said my name was %d. Favorite number, 12. Well, it gets the number right. Turns out that I can do this. Let's try showing everything as pointers. We get a whole bunch of things that look like pointers. And if I go back to the code, this printf here didn't have any arguments. But it's printing out pointers because my thing that the format string that I've given it has told it to print out pointers. So the question is, what pointers is it printing? Now the arguments to a function are usually stored underneath its stack frame. So printf is just going to look below its stack frame to find out all of the pointers that I'm looking for. If it wasn't passed any arguments, it'll just keep going until it finds something it can see. And so what I'm actually looking at here is all of the information in our main function, our greet function. One of those pieces of information is, I believe it is at %. I can specifically say get me argument number 70 and show it to me as a pointer. That pointer there tells me exactly where something in my stack lives. It tells me where the stack frame for main is. Once I know that, I know where everything else in the stack is. And I can deduce it all because I have a copy of this program, so I can map it out. So once I can use this to figure out where everything in the stack lives, its exact address, my challenge is, I want to get some code, I want to find out where everything is, and then I need to somehow insert my own program on top of this and tell the computer to execute it. Nice way of doing this is I have this buffer here, this second buffer, which seems pretty innocuous and not doing anything. I can fill that up with my own code, and because I know where that buffer is, I can go further down the stack and edit that value that says, when you finish this function, go to here. And instead of this function returning to main, it will move into this buffer and start executing. We'll take a look at what code like this does. So the code that I want it to run here is a program. I have written assembly, which looks basically like this code here. It just says we're going to look for a program called GNOME calculator, because I want to get a calculator. This is where you should show it. And then start running that program. execv is just a special function that says, destroy this program, do this other one instead. This is what the assembly version looks like. This is how your computer reads code. This is the code your computer understands. Kind of. That's how we write it so that we can still kind of read it. The way your computer sees it is just as a whole bunch of numbers. So this array of numbers is that program. My challenge is to get that array of numbers, stick it inside the program I'm talking to, and then get it to run it and replace itself with a calculator. So what I have here is all this program does. If I run hack, it just says, please type %70p and press enter. Okay, %70p. And it spits out a whole bunch of junk. And this junk is the code that we want to run. That's how code looks like when you compile it. Bit of a mess. You can see some of the text that I was trying to write there. Looks a bit weird. But what happens is, if I take this and I just say everything that this program spits out, spit it straight into our vulnerable application. So the first thing this does is it says, my name is, please type $70p and press enter. And our program says, nice to meet you, please type that address and press enter. So I type it in, and it turns into a calculator. I'll just go back and look at the code. This is my vulnerable program. Nothing in here is saying to execute a calculator, right? It's just reading in some things and printing out some things. This is the program that I've used to hack it. It's just printing out a bunch of text. Prints this out, does some calculations, and then prints this blob of data out, overwrites some stuff in the stack. When I pipe one into the other, it starts to do some weird stuff. FFC7, 2, 6, F8. I hit enter, and because I've managed to overwrite some very specific values on the stack of my program, I've turned it into a calculator. Now, this might seem pretty basic, but you need to have the program running, and it needs to be sitting next to you, and you need to have both of them, but you don't, right? If I can send any form of data into your application, so you're writing maybe a web server or a web application, and I have some control over some form of data that gets sent into that, you have maybe a web form that I can type stuff into and I have control over. If you don't check that properly, maybe there's a way for me to send a specific piece of data so that I can start running software on your server, and you probably won't notice. I could run a crypto miner, start mining some Bitcoin for myself on your server. The point is, it's very easy to make some of these mistakes, but if you're careful, it can also be pretty easy to catch them. We've done some done some work to make it a bit easier to make sure that you don't have these sort of bugs. So for one, when I type make, there's this whole bunch of extra stuff. Basically, it says all of the things that you would normally do when compiling to make this code safe, don't do them. So these particular bugs aren't ones you should run into. Also, if I say use DCC instead, so I compile with DCC, it won't compile. DCC gets very upset. That's just ASAN. But then if I try and run it, it'll also run to other things. So DCC does help a bit. Compilers help a bit, but you still have to be wary. So basically, in the case of this one, I've just used two things that I should never, ever use. One, never use gets. Two, like if I was going to write this as a nice printf, there is no reason I can't just do this. And then that is fine. And this should be fgets. Fgets, so this is complaining at me now because it has too few arguments. So I need to say I need to say where I'm storing it, the size, and stream. So buffer length, and then stand in. And I do the same down here. Now if I compile this again, and I try and do the same attack, nothing happens. I just get cent, $70p, and I just get my favorite number as 1. And everything's safe. Yes?
Is the reason f gets is safe is that you can't like close off the bullet because you're limiting it?
Correct.
You have the number,
So
you have the maximum.
the question we just got was, is the reason f gets is safe is that we have a number which tells f gets how long our array is, which stops f gets ever writing past the end of our array. And that's precisely why f gets is safer than gets and why you should never use gets. Any other questions? I'll hand it back to Andrew at this point.
Okay, is that enough beeping to stop you now? Oh, sorry, just a sec. Oh, that might be better. Okay, cool. Yes, hello. Hello and welcome back to the exciting COMP1511 lectures. Hopefully you found Curtis's stuff quite interesting. You don't have to know how to do it. You don't even have to know the details about it, but you just sort of have to be aware of the fact that if you do things like let someone enter as much as they want into an array past the end of the array, then bad things could happen. This is sort of like I did not mean to click that. This is sort of like the original paper that was written about that, so it's linked on the slides if you want to read that. But next up for something that I reckon is really cool, and hopefully you do as well. Who remembers the far-knuckle exercises? Who does not remember the far-knuckle exercises? A couple of people. So, those of you, so for those of you who entered AIs in the leaderboard and spent a long time watching the leaderboard obsessively and spent your entire mid-sem break just playing in the leaderboard and writing your AI, which of course was not what I did, you might have noticed, right, if you look in the leaderboard, the students who came like first, second, these are really amazing numbers, right? Like getting a number this low is really fantastic and like the mathematical limit of what's possible. But then if you look even higher on the leaderboard, you'll see that Curtis has just slightly beaten me, so we'll just ignore that. But my AI, so for those of you who didn't follow the AI thing, your AI had to guess the hidden sequence of tiles. So the computer goes, I've got a hidden sequence of tiles, make a guess, then it says you've got this many aquas, this many fine aquas, and so on. And so this was the average number of guesses that it took your AI to solve the hidden sequence. And doing it in less than 5 is like mathematically impossible, right? So I had a student email me a while ago and be like, can you show me how your solution works sometimes? I really want to see it, so yes. I will show you my solution now. So, oh yeah, I just have some slides with pictures. Like, these students were very, very, very impressive, and you should not feel bad that my score was better because I cheated. So, thinking about what you know about stack frames and stuff so far, right? Like what we've just talked about. I did put the links in here. So I've got a PDF. I'll just use Squidge. I think it's this one. Cool, this one will do. So if you look at this is the code that actually ran the tournament. So this had the main function, so the thing that would run your code, not your code, had a main function with the hidden tiles, then had a function that called your AI and said, give me a guess, and gave it like all the previous guesses and the previous fine aqua counts and so on. So then your AI filled in this guess array. I've got code printing out the AI guessed this number here. And then if the number of funarcles in that guess is the number of tiles, if you've got it right, then it'll print out you guessed the tiles in this many turns. Right? And then my AI is down here, and we'll just ignore that code for a minute. If we look at the stack frames, right? So looking at these stack frames, we have the hidden, so main stack frame, main function memory has this hidden tiles array, right? And then that calls the test funarcle AI function, which has things in it like the previous guesses, the funarcles, the arcles, all these various arrays and various things. And then that calls your AI. And I think I have that circled down here with a lot of colors. So this here calls your AI. And so inside my AI stack frame, it had all these various things. So like Coda said, your function, when it's called with arguments, those arguments end up below your stack frame. So at this point here, lower down than the things in like the local variables, I have things that I was passed into, like the turn number, the previous guesses. And if I zoom in on this, importantly, in previous guesses, max turns and tiles is a pointer to where the previous guesses array is stored. So in this case, come on, you can do it. The memory address of the previous guesses array was this address here. That's just what it happened to be when I ran it. And so that is the value that's stored inside the previous guesses variable in my AI function. Is this all good so far? So I am given a pointer to the array in the other function. I don't have the array itself, I have a pointer to it, so I know the address of where it is. And I also happen to know that the space between this array and the hidden tiles in the main function is exactly this many bytes away. And so if I know where the guesses array is, and I know that if I go down another 2,656 bytes, that's where the hidden tiles array is, what could I do with this? Rather than guessing the values, I could just read the answer from main stack frame. I could just go, okay, I know where the answer is stored in memory. The answer is going to be in this hidden tiles array. Let's read the values from that, and that's the answer. And so this is my code over here. I've removed some of the irrelevant stuff. You'll notice that we didn't have a score of 1 on the scoreboard because it'd be really obvious that I was cheating if I always guessed in 1. So I made it have a thing that decides how many turns it should take to guess the thing. And if it's decided it's gonna, it makes some number of random guesses, and then after that, it does the actual work. And so I have this offsets array because the number of tiles would change, and so if there were 4 tiles, the offset was 2,256 bytes, whatever, and so on. So the number of tiles you had changed the distance between the hidden tiles array. I worked these numbers out with trial and error. I then make myself, this line of code is quite confusing, and it has a thing called a called a typecast. Let me scribble on this with a pen. So what I'm saying here is take the previous guesses thing, and this is the address of where this array is in the function, right? So that's this address here. Add on the number in this offsets array. So add on this one here, or whatever one it was. That is going to give you another memory address. So you need to say it's a memory address. Int star and circle brackets means I'm saying that this number is a pointer to an int. And so then int star array is going to hold this address. And then I have a copy tiles function that just goes through that array and copies the things into my guess. I've got a bunch of, a bunch of printfs here that would just print out what's going on so you could see. So it decides to guess the right answer this time. It prints out the address of the previous guesses thing, and so it knows, based on this, I know the hidden tiles array is going to be at this memory address, and then prints out the 4 values. So basically, whether this is cheating or not is sort of, it's nothing in there said that you had to not do this. But does this sort of make sense? Based on the way that the stack frames are laid out, based on the way that the kind of functions are called and the way that everything builds up on top of each other, I was able to go, I can just work out where the answer is stored in the main function. and then just read that answer out directly. Is that cool? Who thinks that's really cool? A couple of people. Do you know how many hours I spent on this? I'm not even going to answer that. My family were very upset. Would you like to see me run the code, or are you happy with just having seen this? Does anyone want me to run the code? Okay, yep, I figured. So this is basically the same code. I've added some more comments or less comments or something. But I've also got the code that actually runs the tournament. Test, simplified, simple. Not quite. Cool. So the way that the AI running thing works, you give it, so the person running it gives it 4 tiles, then the AI makes guesses. And so in my AI, I've gotten like a printf up here. If it's going to make a random guess, it prints out making a random guess, fills it with a random guess, and then returns. So you can see it's the first 3 times it said I'm going to make a random guess. And so it's guessed these 4 values. And then on the 4th turn, it's decided it's going to guess the correct answer this time. I'll move that up a bit. So I've got the value inside the previous guesses variable, which is the address of the array stack function in the other stack function. I know what the offset is, so I add on the offset to this, to the address. I get this new address, and then I look at the places in that new address. And so I had a lot of questions about stars and ampersands and arrows and stuff. What I've got here, star means dereference, which means go to the memory address that is here and get the value. So in this case, it goes to the memory address that is in this variable array. And that memory address is this number we calculated here, previous guesses plus the right offset. So go to the thing that's at that address and get me the value. So the star means go to that address, get me the value from that address. And then this +1, +2, +3 thing here I have means go to that address in memory, go across 1, and then get the value there. So that's like getting the 1, 2, 3 array element indices. And then just to prove that it'll guess it in 1 if I get rid of the thing where it doesn't guess it in 1. Cool, so if I enter the tiles 1, 2, 3, 4, it guesses it in 1 turn. 1 turns. If I enter the tiles, those numbers, I guess them. I reckon that's pretty cool. Do you reckon that's pretty cool? Yeah, I reckon it's pretty cool. I think that was about it in terms of the slides. Let's have a look. Cool. And so now let's look at questions. So I can see the 17 questions so far. I might refresh that page just in case. Okay, just 17. So having read through these, so I guess I can, a couple of people have asked about the exam. I can answer that one quickly. We'll tell you about the exam next week in the week 13 lectures. And until then, we're not really going to answer questions. So I'm sorry about that. But we will tell you all the information in week 13, which is next week. So that would be great. I had quite a few questions about Malloc and stuff. Let me find those around here. Oh, memory heap stack significance summary of Malloc. How does Malloc work? I have slides for that. Diagram. Draw on screen. Cool. So this is sort of the memory layout diagram, right? I might actually draw a new one. Cool. So here is a sort of wide overview of memory. So the way these numbers work, this is a very, obviously this says 0x00000000, very clearly, and this is 0x all f's. What this means is the low numbers in terms of memory, like if your memory address is a smaller number, it'll be towards the top, and if it's a bigger number, it'll be towards the bottom. Different people have different opinions on how you should draw this. I am adamant that my way is correct, and so it should go up this way, but be aware that some people draw it upside down. So we have sort of like the heap, we have sort of like the stack. I said your code was here, and I've said there's magic here, and there's magic here. So, and importantly, the stack grows upwards, and the heap grows downwards. So, when you allocate more things in the heap, when you malloc more memory, as it needs to, the heap will grow further downwards in memory. And as you call more functions, as it needs to, the stack will go up higher in memory. And then let me draw a simplified version. Whatever. Stack. Heap. Cool. So in terms of the significance of this, I drew that upside down. In terms of the significance of this, so we've looked about stack frames, right, and about how there's information stored inside a stack frame. The local variables are there, but there's also stuff in there that is important other information, I guess, about where the stack frame starts and ends, where you're going to go after the program, after the function ends, and so on. In terms of the significance of this, though, I'm not sure if we've really talked about this explicitly before. If we have a function, right, we have some main function. Here's main stack frame. And then main calls some other function. Hello is a good function name. And then the function hello returns. This might be better with code, mightn't it? I feel like computers shouldn't be this hard. Test, cool. The question was, what is foo? Foo is just a name that you give things in computing. It doesn't have any special meaning, it's just a name, because I couldn't think of a better name. I could call it blah, or hello, or whatever. Cool. So if I add a printf to my code, make this one smaller, here. Okay, come on. So in terms of the stack frames, right? The main function has its stack frame. And stack frames grow upwards, like as you call more functions, they grow up higher and higher and higher. Inside the main stack frame, it has I, it has j. This is all good. It calls the function foo. Foo is called, so it has its own stack frame here. This is for foo, this is for main. Foo will have x is 20. So think of x here with 20 in it. And then foo will return x. And so what happens when a function returns? What happens to the function memory? Someone said it disappears. Yeah, it disappears. It can be reused by the next function that's called. So if we see foo stack frame is here, and then foo returns, whatever function is called next is going to overwrite that memory. So if I now call printf, printf has whatever stuff it needs inside, whatever. Printf is going to be using the same memory that foo stack frame was. So you can see that the stack frame inside that first function, like the memory still exists, right? It's still in memory, but the values in it have been overridden by other stuff. And so this is why, for example, if you tried to make an array inside a function and then return that array. So if we had code that was like, I'll make it be an int star. So this code here will make an array inside this function and then return that array. And so then looking at this here, right, that would be called like this. So here is our function called fn. We have this array inside, which is 10 big. It's called array. When we return a function, we return the address of where the function starts. I'll say that again. When we return an array, we return where that array is in memory. So if it's at address 0x100, and we have it in here, we're saying that this array is over here, right? And then when my function returns, and my next function is called, the stack frame goes on top of that. Right? So my next function might have this stack frame and have whatever stuff inside it. You can see the stuff at this memory address still exists, right? Memory address 100 still exists inside memory. But the contents of it are not going to be the array that you put there. They're going to be whatever this blue function stack frame happens to have in it. So does that make sense?
I actually wanted to ask, because we often ask AI, how did you know exactly what was 2656?
Trial and error. I just tried lots of stuff. The question was, how did I know the right numbers for the final thing? I can look through the code that I used to work it out if you want, but it was a very, very long week. Right, so in terms of the significance of stack frames, right, there's a couple of really key takeaways you need to take from here. Function memory does not exist longer than that function does. If you have a variable inside a function, when the function returns, the variable will be reused. That memory is used by something else. So you can't rely on any memory, any things existing in that memory still. Maybe that's it for stacks, and also there's information you can override. But of course, if you want to make some memory that will stick around for longer, then you can't put it on the stack, right? Because the stack frame is going to go away. And this is the significance of Malloc. Right? So in our stack, we have our stack frame, so like main stack frame here, whatever here, right? And then as a function returns, its stack frame goes away and then is used again by the next function. So we can't put anything permanent here. If we want something to stick around for longer, we need to do something like allocate it with Malloc. And so when we call Malloc, Malloc is basically saying, here is a little piece of the heap. Here is some memory for you. Its address is 1234 or whatever. Malloc will give you that address. Malloc will tell you, this is where the memory is for you. I've set this memory aside. It's just for you. Do what you want with it. Here's its address. And then when your functions returning your stack frames go away and so on, like this spot here in the stack, this is where stack frames are going to be created and be destroyed and all that sort of thing. The stuff up here in the heap will still be safe. So does that make sense in terms of the difference between the stack and the heap and the significance of them? Cool. Are there week 13 lectures? Yes. There will, I think, be lectures both days in week 13. The room isn't booked for Tuesday. We'll try and fix that. Okay, so I guess there are two main things that I should explain next. Two sort of questions that have come up again and again and again. It's not quite as effective as shushing. Two of the questions that are coming up a lot, people are sort of confused about structs and struct pointers, and people don't really know how to start the assignment, like how to use your stuff from the week 11 lab to make the assignment. Which of these do you want me to do first? Assignment stuff? Or stuff on like structs and pointers? Okay, the 10 people in total who voted. I guess I'll start with assignment stuff. So, assignment 3, lab 11. So I highly recommend, if you don't get the lab finished from last week, you can download the answers tomorrow morning, I think, because it's due tonight. But by the time you have finished, this lab exercise, Go West Young Bot, you will have an AI that does the following things. If you're at a place that sells electricity and you need electricity, then buy electricity. So if you are currently at a power place and you need more power, then buy more power. Otherwise, if you're not there, if you're at a place that sells apples and you don't have any fruit yet, then buy as many apples as you can. Otherwise, if you're at a place that will buy apples from you, then you should sell all the apples that you have. And otherwise, you should move as many locations around as you're permitted. I'm going to assume you're all talking because you've finished this exercise and everything is super easy and you're all happy. Maybe you're not, maybe you're just bored. But basically, when you have finished this exercise, you will have an AI that does the following things. It'll, at the current place that it's at, it'll either buy power if it needs to, buy or sell apples if it can, / needs to. And so the way that this bot will sort of work, cool. If this is your world, slightly bigger. It sort of got worse, not better. Oh well. So if this is your, try again. If this is your world, right? This is your world. There are places here. Shall I shush again? Shall I just give up and go home? Like, please be quiet so I can talk and you can listen. So these are the locations in your world. This might be CSE, this might be like an apple growing place, and so on. The code that you will have when you have finished this exercise will go, whereabouts am I? I am currently at this place here, and this place here will sell apples. I don't have any apples on me, so I'm going to buy as many apples as I can, right? And so then you'll go, oh, if I'm at a place that will buy apples from me, then I'll sell them apples. If I'm at a place that will sell power and I need power, then I'll buy power. But sort of the key thing here is if none of these things are true, if you're not at a place that will buy or sell apples or a place that will sell you power, then you'll just move west as many locations as you can. What's the problem with this? Why is it not sensible to move west as many locations as you can? Yeah. Yeah, you're wasting power. Like, if you have apples in your inventory, if you have bought apples before and now you have apples, and you're not at somewhere that will buy apples, what should you do? Yeah, you should find somewhere that will buy the apples from you. So if you are at a place that sells apples, for example, and you've just bought some apples, rather than moving somewhere at random, you should move to the closest place that will buy apples from you, for example. So does that make sense? The number one place to start with this assignment would be take this code you have here and then make step 4 be a whole lot smarter. And then you can do things like modify your code that just looks for apples to look for other fruit and various things like that. But basically, deciding where to go, making that smarter will make a huge difference to your AI's strategy. And then conveniently enough, when you have finished your where can I charge one, you will have a function that lets you find the nearest place that sells electricity. And maybe you can change that to do other useful things as well. I think someone had a question on like how do we combine these things together. The way that you would do this, your code inside go west young bot. Right, so when you have written this, you'll have heaps of code in your print move function. And this is sort of like your main function in this assignment. So it's like how in intensity you had like the choose cards to discard, and then you had like the choose card to play function. And we called one of those functions. So again, we will sort of call this function of yours, and all of your logic should be in here. This should call other functions and various things. And then at the end of this, it should print out the move that you want to make. So you can call functions like your nearest electricity one. So you could copy the code from your nearest electricity file, copy that function into here, and then call that function in here. So you might say something like, I guess I'll just write a button there. So you might decide if you want to find the nearest electricity station, then you could go like nearest equals call your electricity function, and then printf move the nearest number. I don't think I even spelled that right. But does that make sense? So inside here, you can call functions that you've written that will give you information, and then use that information to decide what to do. So if you've decided that you want to get more electricity, then you can call your function to find the nearest electricity place, and then make your move command be move whatever that gives you. Cool. Does that make sense? Then another question, what is the first step you would take in devising the bigger picture for what functions you need? Strategies to do this efficiently. I guess for this sort of thing, like, how do you decide what your strategy should be, right? I would say play the interactive one, get a sense for what the world is like. So do things, go around buying and selling things. Because it's really important that you understand the problem before you try and solve it. Like if you're trying to solve some problem and you don't really know what you're trying to do, then how are you going to solve it, right? But if you have a really solid understanding of this is what I'm trying to do, like if you've played the game Intensity, 100 times with your friends and you know really solidly, this is my strategy when I play, like as a human I've worked this out, this is what I do. If you can work out that sort of thing and have sort of a bigger picture strategy plan. So like for Intensity, I think my strategy was along the lines of get rid of the really big cards when I discard things, but if I have a few cards of one suit, get rid of all of those. And then my strategy for playing a card was like, if no one's going to play a calf or whatever on me, then I want to win this round. And then like if I know someone else has the buffalo, then I don't want to play a higher 40 card than that, and so on. So I sort of, myself as a human playing it, worked out what my strategies were. And then I sort of went, how do I write these into code? And I guess you sort of break the problem down into things. So like with Intensity, it's like when you're choosing which card to play, you sort of got to work out what was the first card played this round, and then based on that, what am I going to be doing? If that makes sense. But basically, work out what the problem you're trying to solve is. So understand the assignment really well. Understand what the world is like, what sort of moves you can make, what's good to do when. Think about your bigger picture strategy, and often that could be useful to break down into steps, right? Like, ooh. If I scroll, I get lines. That's cool. So in terms of your go west one, right, this is, when you finish this one, you'll have sort of 4 if statements, I guess. Like if you're at a place that will sell electricity, buy electricity, whatever, you want to sort of work out for yourself in your bigger picture strategy, what are the things you want to do? Like you might think, if I need electricity, then find the nearest electricity place. If I don't have anything to sell, then find somewhere to buy things from, and so on. So sort of break your strategy down into the possible situations, write code for those, and then life should be good. And in terms of determining which functions you need sort of break the problem down step by step by step. So how do I solve this problem, and then make a function that goes, how do I solve that problem? And there's a really good ed post that I wrote on this that I can put up somewhere maybe. So I guess probably structs and struct pointers is next. Are there any other questions about assignment stuff before I move on? Yeah? How do you know how many things there are in the world? So you can get information about the world by having a loop that goes around every place in the world and then looks at, for example, how many petrol stations there are, or how many people buy fruit or whatever. Does that make sense? Cool. So let's talk about structs and struct pointers. I might even have lectures on this. So I guess if we revisit structs at a kind of higher level, right? When we have a struct is a collection of different types of data glued together. Yeah? I think someone in the forum said you aren't guaranteed that. Yeah, if you've got questions about the rules of the assignment, the forum is the best place to ask. So when you have a struct, or before that, when you have an array is a whole bunch of the same type of variable glued together. So like an array of ints, you've got 10 ints all glued together. A struct is a collection of many different types of things. So a student struct, you might have a ZID, an int, a string for their name, and an assignment 1 mark, for example. And so in terms of like the usefulness of a struct is that we have a way of combining a bunch of data together in a way that makes it easier to work with, I guess. Like sort of, it makes sense conceptually to group these things together. If I wanted to have like an array of a whole bunch of things about students, right? I could have, I've got an example down here of how I have an array of student structs. I could have an array of ZIDs, like I could have a bunch, instead of structs, I could have a lot of individual arrays. I could have an array of ZIDs, an array of names, an array of assignment 1 marks. And I just happen to know that the student in position, like index 0 is going to be the same student. Right, that probably needs explaining better. So when I have an array of student structs, here's my array. Each of these is a struct, so it's got a ZID, name, mark. ZID, name, mark. Right, so I have an array of these things, and each individual thing has a ZID, a name, and a mark. I could structure this differently. I could have 3 arrays. I could have 1 array of ZIDs. I could have 1 array of names. And I could have 1 array of marks. Right, and so I could just say that the person in index 0 is going to be the same for each of these. So like ZID 0 is 3, 4, 5, 6, 7, 8, 9, and then their name is the thing in name 0, and their mark is the thing in mark 0. But it makes a lot more sense to do it in a struct instead, right? Like if you think about, that color did not work at all. Nope. Light purple. It'll sort of do. If you think about it, like it makes sense for a student to have these things that are grouped together. And so it makes more sense to have one thing that represents this student rather than having a series of different things and sort of taking one from each of them to represent a student. Does that make sense? Like one of the reasons we use structs is because we can turn a bunch of sort of unrelated things into one sensible related concept. Rather than having a bunch of different arrays, have an array of student structs and we say a student is these various things. In terms of actually using structs, does anyone know if I had any good code in any of the lectures? Week 10 was probably all linked lists. Yeah. Pointers.c and structs.c. Maybe these will be good. No, okay, I'll just copy this. Cool, so here's my struct code from that lecture, and shall we just chuck some stuff in main? So when I have a struct, right, and all of this stuff in here, none of this stuff is malloc, this is all just things on the stack, so things inside function memory. I have my student struct ZID name mark. I have my, so when I'm actually making a struct, right, with this code here where I'm making a struct, I'm saying make me a thing of type student struct called Andrew. So here is one student struct. It's going to have the ZID, whatever, the mark 94.5, and the name Andrew. You can just pretend that you can read that. And so this is, no, okay, that really needs to be better. Is that green going to work, maybe? Why don't I clear this so that it's black? Yeah. Possible, delete. Cool. So this line, struct student Andrew, means make me an instance of this struct. Give it the fields, so it has the field ZID, name, mark. Right, the ZID is 1234, the name is Andrew, the mark is 94.5. And so in this instance, this is called Andrew. In this instance, I have made myself an array inside the function's, I've made myself a struct inside the function's memory, and I've put the fields into that struct. So I use the dot notation. I say Andrew.ZID because I'm getting the ZID field from a struct. And when I say a field of a struct, I mean like a variable inside a struct, right? So this struct has an int, a char array, and a double. So when I say a field, I mean like Andrew.ZID means get the ZID variable component, whatever, from the struct. I use the dot because it's right there. It's a struct. I'm accessing the struct. Right, and a common question is sort of like, when do we use the arrow thing? Because we learn them all at the same time and life is confusing. So let me write, copy, struct one. So if I modify this function to, instead of making me a struct inside the function memory, malloc me a struct. So give me some memory from malloc that I can put this into. And so the difference here, rather than having a struct student, I have a struct student star. So I have a thing that will contain the address of a struct that malloc has given me. Size of struct student. Cool. And so this line of code here, compared to this one here, what I've done in this line here, I've made a struct in function memory on the stack. In this line here, I've made a pointer to a struct on the stack, and malloc has given me some memory. Malloc has made me some memory. Now, because this is a pointer, right, I can't say Andrew.ZID anymore. If I say Andrew.ZID, it's going, this is a pointer, not a struct. Like, there's no ZID field. What are you doing? This is weird. This is crazy. You can't do this. Because it's a pointer, I need to dereference the pointer. I dereference the pointer with a star. Is this going to work? Is star Andrew.ZID going to work? The answer is going to be no, because otherwise I wouldn't be asking the question. Clearly that's why these questions exist. Struct one malloc. Man. Okay, in theory. Structs.c. Oh, it's giving me a compile error. Okay, that's nice. So let's just ignore that because it's telling us what we want to be doing rather than telling us why it's a problem. So we can't we can't say star Andrew.zid because we're trying to directly reference a field inside a struct. Let me try doing it this way. So when I have Andrew, Andrew is a pointer to a struct somewhere else. Like Andrew is an address of a struct in Malloc land. So over here in Malloc land somewhere on the heap, right? I've been given memory for a struct student, and then in the functions memory, the thing I have called Andrew is now a memory address rather than a struct itself. Right, so Malloc might have told me it's at memory address 0x1234, and so this thing here will contain that memory address, right? The value of this, I don't know how that happened. The value of this variable, like the contents of this variable, are the address of where the struct is in Malloc memory. And so because of this, we can't say Andrew.zid because that's trying to get a ZID field of a pointer. Pointers don't have like struct fields, right? So that's not a valid thing to do in terms of the C rules. But I can dereference a pointer with the star notation, right? So just like how if I had, go away, like int I, right, is 10. Int star p, to be a pointer to I, is equal to the address of I. So this is now saying I have a variable I in the function memory, in the stack frame, and I have a variable p whose contents are the address of that, so that p knows how to get to it. And so then I can say star p equals 20, and the star means go to the memory address that this contains, so go to the thing it's pointing to, and then change its value to 20. Right? And so then similarly, for getting a struct, I do the same thing here. I say dereference this Andrew struct, so go to the thing in memory where this Andrew struct is and get the ZID field. And if I didn't mess up my syntax, which I might have done because nobody does it this way. Yeah, okay. So it doesn't like that I haven't told it what Malloc is. It compiles. We didn't print anything out, that's boring. But you can trust the lack of compiler errors to mean that this is totally valid. So what I've done here, Andrew is a pointer to a struct. I've dereferenced Andrew. Now I have an actual struct, and I'm getting the ZID field from that. This is really, really annoying to type. And so because it's annoying to type, we have some different syntax. Andrew arrow ZID. And so what this will do is exactly the same thing as this. Andrew arrow ZID means dereference this Andrew thing, go to the address that Andrew is pointing to, and get its ZID field out. So the arrow notation you use when you have a pointer to a struct, and that means go to the struct that this points to and get the field from that. The dot notation you use when you actually have a struct, so whether you either have the struct in the function memory or you have the struct because you've dereferenced the pointer yourself. Does that make sense? Was anybody confused and is now no longer confused? Okay, a couple of people, cool. I've achieved something. So I think it's just about time to wrap up. I know that there are lots of other questions that were asked about a range of topics, and I think I'll cover some of those tomorrow if I can. But otherwise, tomorrow we have some new, fun, exciting themes. If you have any more questions, feel free to come up and talk to me. Otherwise,